Welcome back, aerosexuals, to the RNP AR mini-series, where in part one, we introduced the idea of an RNP AR approach where it's effectively allowing aeroplanes to thread the needle through terrain that's rich in mountains, or it might have obstacles that would prevent a traditional type of approach being flown, whether it be 2D or 3D, like an ILS or GLS. In this part, we're going to talk about how RNP AR approaches are mechanically designed, and then at the end of the video, we'll talk about how it's fundamentally changing the industry. So at its core, RNP AR stands for Required Navigation Performance Approval Required, and what that's saying is that the aeroplane is required to, within a given probability of time, in this case it's 95% of the time, be able to guarantee that it's flying a lateral and vertical band down a GPS pathway. Now, that lateral and vertical pathway that the aeroplane has to be guaranteeing that it's inside throughout the approach varies depending on the approach. And at its basic level, you've got a 0.3 RMP, and all that's saying is that the aeroplane has to be within 0.3 nautical miles left and right of the band at all times. If you exceed that, then you'll get an alert. That's part of the onboard alerting system, and you'd have to abort the approach unless you can guarantee that you're coming back to the approach in a very quick amount of time. That 0.3 RMP can come all the way down to a 0.1 RMP, and that's as low as it gets in today's technology. Now, on many approaches, we've got different degrees of RMP published for the same runway, and that may be all the way from up at a traditional 0.3 RMP all the way down to 0.2, 0.15, and 0.1. And you may be wondering, why would anyone ever select a higher degree of RMP to fly with inferior minimums for visibility and cloud base when we can just choose 0.1? And the reason for that is because we're self-inflicting a requirement to be extremely tolerant on our way down the approach. And on a clear day where it's likely that we'll get visual at a high cloud base or there's very good visibility, to choose a higher RMP like 0.3 gives us a lot more wiggle room on the way down the path. Now, that's not the end of probabilities when calculating RNP AR procedures. Traditionally, when we're flying from a final approach fix all the way down to the MDA, it's quite a straightforward obstacle terrain clearance method. So they use 250 feet from the FAP all the way down to the minimums where you would get visual, and you guarantee that 250 feet clearance all the way down. Now, in RNP ARs, they use probabilities, and what they do is they use the root sum squared of 4 critical errors that would decrease the amount of terrain clearance for the aeroplane. Those 4 are altimetry system error, pilot slop or flight technical error, a long track error, which is basically the assumption that the aeroplane might not be exactly where it is along the approach path, and temperature error. So what it does is it gathers all those together and then root sum squares them together, making an assumption that all of those errors aren't going to happen at the same time. And what that does is, rather than giving us a very simple 250 foot clearance down to the minimums, it gives us a probability outcome where it says less than 1 in 10 million flight hours will there be a contact with terrain on that approach path. So that's the basic mechanics of how obstacle clearance is maintained in the design process of these procedures. Let's talk about RF legs, or radius to fixed legs. And these are really the characteristic that differentiates RNP AR procedures from everything else to date. Probably the most defining characteristic of RNP AR departures and arrivals is the RF leg, and all that is a radius to fixed turn, where you've got a waypoint on your arrival or departure, and the aeroplane's going to maintain a fixed radius turn around that waypoint at a maximum speed, because of course if our speed is higher, our radius turn increases. So we've got max speeds published, and that'll contain the aeroplane in a corridor, usually between mountains or terrain, which otherwise would be impossible. You'd have sort of duck and dive segments of the approach where you'd have at or aboves, but because of this defined radius turn, we're able to thread our way through the mountains using these RF legs and waypoints. The last part of mechanics that I'll talk about is the last 2 letters of RNP AR, and that is the authorization required. And that's very simple. All it's saying is that the aircraft has to be certified, the crew has to be trained, so they're going to have to be part of a training system within an organization where they're upkeeping their skills for these procedures. And lastly, the database. So these are GPS, FMS procedures, and of course, imagine if your Google Maps or your Google Earth was a year out of date and you're trying to fly an RF fix through mountains, it's not going to be very good. So we have to have up-to-date waypoint, and that will usually be updated monthly. Now, if you've made it this far, well done. That's the mechanics done. Now I'm just going to go over really how I think that RMPs are shaping the world and changing the industry. And the reason for that is really the economics of implementing, designing, and maintaining a RMP procedure versus traditional ILS and GLS approaches. Now, if we just look at the raw cost to install an ILS or a GLS approach, we're talking for an ILS in the millions, $1 to $5 million. For a GLS, it's less, but it's still a lot of money. We're looking at about $500,000 to $1 million. To get an RNP AR procedure designed, we're looking at 50 to 150 grand US, which is an order of magnitude at least lower than an ILS. Now, will RNP AR procedures take over entirely from ILS and GLS? And the answer is no. The reason for that being they can't do Cat 2, they can't do Cat 3 autoland. So although it's quite impressive, we can do these curved procedures around mountains, we can get down to a relatively low minima for a non-precision approach, it's still not having that guaranteed ability to land usually on the first try when, for instance, there's sea fog or something like that, which really starts to impact international flights and also has downstream consequences for efficiency because of your ability to carry less fuel if you're flying to airports that do have these precision approaches. But aside from that, the major upside of these procedures is that it's massively changing the connectivity of cities and airports around the world, particularly in low density countries like Australia or Canada or even parts of New Zealand, where it wouldn't make financial sense to be spending $1 to $5 million on a small town airport just so they can get a few jets in. But now that we've got this technology, which is an order of magnitude cheaper to implement, it's opening up aviation markets that otherwise would have been inaccessible. Alright guys, that's it for RNP AR procedures. I hope you gained some value from it. If you want me to cover a different topic, whether it's Boeing or instrument procedures or anything aviation related, drop it in the comments. I'll do my best to shortlist it for a future video. And if you haven't checked out my YouTube yet, go and have a look there because that's where all the long version of these videos gets uploaded. So once again, thanks for your time and I'll see you on the next one.